might have seen a lot of questions like these before, and it is really annoying at this point, so this video wants to solve them once and for all. Before I tell you the secret, please watch the previous video titled Untold Connection, Lagrange and an Ancient Chinese Problem, because you need it to understand the content of this video fully. The answer to these types of questions is anything, literally. And there are two reasons backing this up. The first reason concerns the definition of the term sequence. According to Wikipedia, a sequence is an enumerated collection of objects in which repetitions are allowed. And like a set, the same elements can appear multiple times at different positions, and order matters. These two excerpts are basically paraphrases of each other. The idea is that a sequence is a collection of objects, where the order matters and repetitions are allowed. These 3 points in defining a sequence does not prevent stuff like these. It is a collection of objects. These objects are arranged in a particular order, and while no repetition is here, that does not violate the definition of a sequence, because the definition only says it could have repetition. Even if it is specified that it is a sequence of numbers, you can still put any numbers there. It is still a valid sequence. Perhaps the teacher will say you need to find the pattern in the numbers. But what exactly is a pattern? Consider this sequence of square numbers. Can you articulate what is the pattern underlying the sequence? Using words might be clumsy, so we denote Tn as the nth term. In this case, the nth term is n squared, so we have Tn equals n squared. Instead of saying some clumsy words to explain the pattern of the sequence, let's just define the expression of Tn as the pattern of the sequence. That means even for this very weird sequence, as long as I can find the complicated expression of Tn, I have found the pattern of the sequence, no matter how complicated it is. So the problem is how I came up with Tn even for this weird sequence. That leads us to the second reason for having anything as the next term of the sequence, Lagrange interpolating polynomial. In that previous video, we discussed Lagrange polynomial, which solves this set of equations. Basically, you want a polynomial that when you feed it with x1, it outputs y1, x2, then it outputs y2, and so on up till xn having the output of yn. That is actually really close to the sequence problem. We need t1 to be the first term, t2 to be the second term, and so on. This is basically of the form of Lagrange polynomial, where x1 all the way to xn are replaced with 1, 2, 3, 4, then y1 all the way to yn are replaced with the terms of the weird sequence. The Lagrange polynomial can then be calculated by this monstrous formula. Although the formula looks horrible, the rationale behind it is quite easy to grasp. We just need to change the variable from x to n to write down Tn directly. Of course, you never want to plug in the numbers into this monstrous formula directly by yourself, so I put together a Google Doc on how you could access the tool to the Lagrange polynomial linked in the description. That means whatever you put as the next term in the sequence, here let's say 1, 2, 3, 4 are the given numbers, you can still put anything you want. And according to the tools that I detailed in the Google Doc in the description, you can still get Tn for the sequence. I hope this video really solves this type of questions once and for all. If you enjoyed this video, like and share it, and subscribe with notifications on so that you don't miss any new videos. See you next time!